Yeah, hi, I'm Alan Fetters with Alaska Energy Authority. I work with David Lockhart, and what I'd like to do is show you some SCADA from Unintended. Let me get the presentation started here.
Yeah, you seem to have a grasp on that.
Okay. What we have is right now, you got a laser here. Okay. Shine my eye. Okay. So this is live SCADA from Unintended. And right now, as you can see, we're live right now. And there you go, David. He decided to cut out just when it started. This is live right now, and as you can see, there's 6 turbines. I believe 5 are running. We'll get to that in a minute. And I don't know if you can see that number right there. That's 436 kW right now. And the generator load, which would be from right here, is 263 kW. So we're above 50% penetration right now. This system consists of 4 Cat 3, 4, 5, 6s that are, I think, rated at, as I say, 475. And we have I can't remember the size of the boiler. I want to say it's about a 300 kW boiler. Okay. We have a station service, and then the bus, the actual community bus, is divided up into 3 sections. So this is the community. This right here would actually be the distribution system in the community. And the wind is hooked into the distribution system, not into the powerhouse. So if we go into the turbines, you can see here, this is the individual turbines, and this is something Northwind will probably present more on you this afternoon. But these are the individual turbines. One is obviously offline right now. We believe this one needs to be have the blades balanced, or it needs some additional effort. But as you can see, these individual turbines, the wind speeds are right here, the air temperature and the wind speed. So right now in Unintended, the wind's blowing. It's blowing quite strong. We're getting nearly full output from each one of the 100 kW turbines. We've got 92, 96, 76, does that say 100? It's close to 100. And then 90 something. So we're getting almost full output out of the wind turbines right now, obviously with the exception of one being offline. And most of that energy is going into the bus. There's only, at this point, we're using 26 kW from the turbines. Well, 26 kW is being used from the turbines and going into a boiler that's, I'll show you in a minute, that's hooked into a district heating system, okay? So we use that boiler to help stabilize the load, and if the demand of the community is lower, we raise the input to the boiler, and we're fine-tuning that right now. We just got this perfected or got online here the last couple days. And we've had it online. The wind's been online a long time, but we just basically got this system online the last couple days and perfected. So as you can see right now, we have 215 kW bus load and nearly 431 wind. So that's quite a high penetration. The boiler, what we're experimenting with right now and working with Northwind, is allowing the boiler, we kind of pick a set point, and it helps stabilize the grid. It moves up and down, but we don't ratchet the boiler up in heat, in load, unless the diesel generators, we have like a 20 kW deadband. So that way we stop the diesel engines from hunting all over the place, trying to follow the wind around. So if the wind's pretty steady, we kind of try to keep the diesel generators within a 20 kW band. And if the wind dies down, then we pull load from the boiler, and then we step that down, and the diesels can ramp up. But that's kind of our PID loop right now on this. David, do you want to come up and start your presentation? Sure. I'm just trying to fill in some time for you. Go ahead. You're good.
So I'll just introduce you very briefly. David, as worked with the Alaskan Energy Authority since 1994, managing various things. And I said he's the lead engineer for Alaska Energy Authority's World Energy Program and holds a master's degree in mechanical engineering from the University of Wisconsin Solar Energy Lab. Please, floor is yours.
Thank you, Pierre. Well, I always try to do something a little different at the beginning of my presentations to grab people's interest, but that's the first time I tried that one. It seemed to work. Well, Alan's going to help me with this presentation, and I really appreciate his assistance on it. I'm a part-time Powerhouse project manager. He's a full-time Powerhouse project manager. So I'll just jump right into this. These are the goals of the presentation. I'd like to leave you with two general ideas or significant ideas. One is that these power systems in rural Alaska, it's one system. The wind, the diesel, the distribution system, and the loads, and the heat recovery, it's one system. And one of the things that I've noticed in recent years is that it's less successful to work on one aspect of it without actually incorporating all aspects of it. The second idea I want to leave you with after my presentation is that many aspects of these systems are changing dramatically. I'll talk about some of the technology that's changing, but the villages are changing really fast, which makes it hard to hit that moving target of the loads and the needs in the communities. So this is really my presentation right here. Everything else just bolsters these ideas. And the numbers that I've got here are in some cases based on empirical data, but in many cases a good estimate from an engineer, not necessarily me, but some of the consultants we work with, and Chris Noonan in our office. Al and I both work for Chris when we're doing Powerhouse work. So to start off with heat recovery. Might sound like a really old idea, maybe something that's not changing very fast, but I'll show you some of the applications that we're working on. Alan's taking the lead on some of these. They're changing pretty fast. Traditional jacket water heat recovery from a diesel has an impact on estimated fuel savings of wind turbines of approximately 10%. So that's the low end of the range you see there is traditional jacket water. And that's often providing heat to a school or some load like that that's seasonal as well. There's three technologies that I think of. After the jacket water comes a wet manifold or a marine manifold. I'm going to show you some photos of something we've been using in that area, which typically will get you 15 to 20% impact on the savings from wind energy. And maybe I should explain that idea. When you provide a wind kilowatt hour and it offsets a diesel kilowatt hour, it also offsets the heat recovery that comes out of that, because the majority of the energy in a unit of diesel fuel actually goes up the stack or out the radiator rather than produces electricity in one of these powerhouses. And then the final technology that is being used in a number of places around the state and probably will be used further, and that my agency is doing some field research on, is stack heat recovery. Diesel efficiency, I'll show you some curves, efficiency curves. We estimate the range is probably 0 to about 30% impact on the generator efficiency of running generators at low load, which is often what happens in a wind diesel scenario. Station service, I don't have a lot of good data on this. I'd appreciate it if somebody in the audience does. It's not even clear sometimes whether there's a station service meter on the wind turbines themselves. But this is a range that we've seen some indication of 1 to 8%, and it goes for things like resistance heaters to keep the controls warm and reduce condensation on and impacts on the controls. Warm transmissions where there is a transmission, meters, and then startup power as well. Power factor correction. Often in these projects, there's a need for power factor correction. It can actually be exacerbated by high wind penetration. We've seen this in Uniloclete. There's some large induction motors at the fish processing plant there, and because the wind turbines produce unity power factor, we've actually, and they're at times have fairly high penetration, as you've seen. We've seen power factors as low as 40%, and there's a risk of actually tripping the entire system offline if the diesel generator can't handle that. Line and transformer losses. This is referring specifically to the distribution line to the wind farm, which is added onto the system for the purposes of the wind project. And then, of course, there'll be transformer losses associated with that, even when the wind turbines aren't operating because they need to be energized. This last category, something that's been talked about, 50% is a rough number, but heating efficiency in these communities is often about 70–80% on an annual basis, which is about twice as much efficiency as you get out of a diesel gen set, and so that impacts the savings if you use wind energy for heating purposes. You want to add anything else?
No, you're good.
This is actually one of the more creative things that my agency's done, and I think Bob Havemeister, Chris Noonan get a lot of credit for this, Brian Gray as well. They designed a custom marine manifold for a Caterpillar 3456. This particular gen set, it's a tier 2 gen set, so it's not legal to install new anymore, but it's one of the most efficient engines that we have found in this size range. And so, but it wasn't available with a marine manifold. So these guys, creative guys that I work with, found a way to retrofit equipment from other Cat gen sets. Right here you can, that dark thing there is the exhaust manifold on the before engine. And over here you can see it's covered up. This is the wet manifold, which has coolant in it. The water pumps on the right side there, and there's a turbo. This is a turbocharger here on this engine, but that we had to replace it with a different turbocharger that's over here on this end of this engine. And we've done quite a bit of testing in our shop on these engines. We found that running it in this configuration doesn't impact generation efficiency, but there is something like a 50% improvement in heat recovery. So it's very significant. You want to add?
You've got a graph coming up on that, right?
Yeah, yeah. So here's, and I apologize, I'll let you know what it says, but at least you can see the lines. The top line there, that black one, is the estimated heating load in Uniloclete. There's a district heating loop there, and it, what does it go to the school and offices and water plant?
Yeah.
So anything, community building? I think though, it's quite a nice heating loop with a high demand. So the estimated annual demand is 85,000 gallons of year. That's the equivalent stove oil heating usage. And then so I'll start at the bottom here. This green line is the heat recovery that you would get meeting that load with a 3456 just jacket water. And this Powerhouse that's recently been completed has got four 3456s in it. 2 of them are standard, 2 of them have the advanced marine manifold on them. So if you just use the standard ones, that's the heat recovery you would get, and that works out to 34,000 gallons a year of savings. You can see in the summertime, June, July, when the school's closed, the load goes way down, and so there are no savings claimed, even though there's heat production, or minimal savings claimed there, even though there's significant heat production. So the blue line is what you would get if you used a 3512, which is what they had in that Powerhouse previously. much larger engines, about double the capacity, and that would produce 60,000 gallons per year of savings. Pretty significant, $250,000 approximately of savings. And then the red line is the 3456 with the marine conversion, which this conversion here. So you can see that from the green line to the red line, there's a very significant change, and that's 71,000 gallons of savings. So more than twice as much. And this kind of goes with that theme I mentioned earlier that the technology is changing. And then, well, I guess that's all I had on that one. Any questions? By the way, I'm happy to take questions during the presentation. I think it's a good way to keep people involved. Alan, you want to talk about this one?
Sure. This is let's call it an experiment we did. This is the Chitina Powerhouse, and what we have here is, this is a John Deere 4-cylinder engine. It's a 117 kW, typical maximum kW output. And typically you would just come right up out of, this is the turbocharger, and these are the cooling systems that we, in the powerhouses that we designed, we would go to a common manifold. In this case, what we did was take, this charge here, excuse me. This is the cooling system that we would typically go to a common radiator or a heat recovery system. This case, what we did, and this would usually be a thimble, just a straight piece of exhaust pipe up to, that's a muffler or a silencer, whatever you like to call it, okay? So instead of just installing a thimble, just a straight piece of pipe, what we did, this is stainless steel. We just had this welded up in town, okay? And it's a double wall stainless steel cylinder, okay? So what we did was, instead of inserting just a piece of straight exhaust pipe and exhausting it out, we actually have the engine coolant circulating through this pipe and then coming back out to the common cooling system to get added heat without the complexity of some other typical exhaust heat recoveries that have clogging problems and something, etc. This inside diameter, there's nothing special about it. It just goes straight through it. Some of the concerns we had are, are we getting any glycol scorching? Is there anything? We want to actually take this off and cut it open and see if we had any glycol scorching on this exhaust manifold. But we estimate, and actually we plan to work with possibly ACEP and put we don't have any temperature monitors or flow monitors on this, but we would estimate, the engineering estimation is that we get about 10% more heat when this engine's running with this configuration. And also, if this were to cause a problem, if we had a problem with this, we would just pull it out, take the hoses, connect them back up to the common cooling system, and we're back in business, i.e. keeping the power on. You know, we have to be careful with when we do this with exhaust systems. And you might be wondering what this little blue tube is on this connected. And each engine has it. That is how we keep the engines warm if they're not running. So if we have another engine in the bank, this Powerhouse has a bank of 3. If this engine wasn't running, we need to keep the stack up, the water jacket up to temperature so this engine can be put on light immediately. So this little bit of this goes back into the engine and circulates the common cooling system water through the engine, so that engine is always at, let's say 180 degrees, if that's what the common rail for the cooling system is at. So that's kind of what that description is. Are there any questions on that?
Alan, do you want to say anything about studying this or gathering
Well,
data on it?
ACP, we're thinking about, I did a little bit. We want to work with ACP and put another one of these into Ruby or Igiage, or come back on this one and monitor it and actually get what the actual BTUs are. Is this worth employing? And is this type of installation worth it? You know, again, it's a small amount of heat recovery, but again, if you're running this engine 24/7 for 5 or 6 months a year, that amount of heat can add up real quickly at $5-6 a gallon for diesel fuel.
And one of the
Could you finish in 5 minutes?
Sure. One of the reasons that there's more interest and more development in heat recovery is that Alaska is going to ultra-low sulfur diesel now, and with less sulfur in the fuel, there's less risk of acid forming in the exhaust stack, and so these systems are easier to make successful. Was there a question back there? I saw a hand up. Oh, yes, sir.
I was just wondering if you estimated the sort of sacrifice in heat exchanger efficiency by not going to a more conventional off-the-shelf heat exchanger, just the space height.
I don't have those numbers, and this is a good question, and you're obviously an engineer. There's so many variables in this. I mean, you could engineer this very specifically and put a lot of controls and feedback logic on it to ensure you get the temperatures you want and all that. Or you can just build it and see how it works. And I'm an engineer. I'm an advocate for designing and engineering things in general. But with so many unknowns and variables, this is an interesting way to get one in the field and start gathering some data on it. So, but I very much appreciate the question.
And not impact the emissions or add any maintenance to the system. Typical other heat exchangers that we've had, a limited amount of exhaust heat exchangers that we've had experience with, come with maintenance requirements, blowdowns, check for soot, buildup as David's suggested. So this was an easy way to recover 10%, we believe, recover heat without impacting maintenance or reliability.
Yes, sir.
Can you explain this, the cooling system that's shared between the gensets? How is that done?
Yeah, maybe afterwards, Dave, you need to get through your presentation? Yeah.
Okay.
Can we do that afterwards? Okay, thank you.
Okay, I actually picked the information off of one of Kat's slides I found online, so I hope that's okay, Kat. Tell me if it's wrong. But I thought this was really interesting and admirable. There's an enormous amount of wasted energy in a gen set that doesn't use heat recovery, and Kotzebue is going to kind of the other extreme in terms of taking advantage of it in as many ways as possible. In fact, I think there's one way I didn't even list here. If anybody knows, please speak up. But their goal is to use 85% of the energy in the fuel. And that is a really valuable thing. But when you introduce wind energy, this reduces the economics, the benefits of the wind turbines. So I wanted to put this slide up to show you that 3456, the big yellow machine I had on the screen a few minutes ago, that's the upper curve here. And for people who are not familiar with diesel efficiency versus power output curves, this is a very valuable curve. Now maybe it's because I'm a mechanical engineer, but I find this fascinating stuff. That engine there has been optimized for power generation uses. And I don't know the manufacturer's explanation, but I suspect that these are probably optimized for maximum power output or for truck applications. A lot of these engines are truck engines. But what you see here is that not only is the curve a very, very different shape, but it's very much higher for this engine. Over 15.5 kilowatt hours per gallon through its sweet spot, which is where you would design it for operation. Whereas you look at these and they're barely breaking above 14. That's very significant. And it's actually one of the points I want to make is that when you're thinking about doing wind projects and the benefits of wind projects, I would encourage you to start with thinking about heat recovery and diesel efficiency, because often there's low-hanging fruit there that can be picked that is very economically attractive. These other engines I've got on here, there's a 3508, the 3512, the one that runs out that far. These are typical gensets you see in use all over the state. Here's a similar type of information. Note the shape of the curve. You don't have that optimized curve on any of these engines. It's not a reflection on John Deere, it's just that these are smaller engines, they're less efficient, and the efficiency drops off faster as you get down to the low end of the curve. I want to make one point on this one. I got a SCADA screenshot from Mark Teitzel of AVIC recently. It was the Kasigluck wind project, and it was showing a real stellar performance. I think it was 280 kW of wind output, and they had a 3456 running at 80 kW load. And so if the diesel had been carrying the entire load, it would have been at 360 which would be right up here at the peak, over 15.5 kilowatt hours per gallon. As it is, it was down here at about a little over 11.5, under 12 kilowatt hours per gallon. So that's some of that effect that we're talking about of wind impacts, unintended consequences, wind impacts on diesel efficiency. Yes, sir?
Is that high efficiency diesel, is that the tier 2 or tier 2?
It's tier 2. And that's one of the other things that's changing. I'll have a little more information on that as well. This, can you see that light blue curve there? That's the 3456 as well. I put this one up because there's one of the Alaskan utilities was looking at replacing a genset, and they thought seriously about installing this one here, Cat C27. You can see it's got, you know, somewhat similar range to the 3456, but oh my gosh, look at that difference in efficiency. The bottom here, this is 9, so through its range of where you would expect it to operate, the difference is between 10 and 30% in efficiency. So this is just the choice of a genset. It's not as if you're, you know, bringing in some fancy new equipment that you wouldn't have bought otherwise. They had to buy a genset. Just the choice of the genset was very significant in this case. And back to my point about thinking about diesel efficiency opportunities, this is FY09 PCE data, power cost equalization. Most of you are probably familiar with it. My agency runs that program. And in the PCE program, in FY09, 1% of the kilowatt hours came from wind, 6% from hydro, and 93% from diesel. So my point is, going back to this one, if you can capture even 10% diesel savings or 2%, the impact is really going to be significant in rural Alaska. Kat, how am I doing on time? Out of time? Okay. Well, I got one more slide. Okay. This is a diesel efficiency slide that I put together. This is PCE data as well. So, you know, there could be some effects in this data that are not apparent. For example, seasonality, when power tends to peak in the wintertime and it's colder, which would affect diesel efficiency. And I also want to show that this scale here is expanded. It goes from 13 to 14.4. But basically, when you go from 0 to 50% efficiency, and if you follow this curve here, there's about a 5% drop in diesel efficiency. And so this is empirical data, which is why I thought it was interesting to show the effect of diesel efficiency. Okay.